we have a presentation by John Donahue from the Beaufort County Sheriff's Office. That they're a Trello user and they've been online since January 2016. And he's going to tell us today about his process and how they're using it to really go through a lot of data down there. So without further ado from me, I'm just going to turn it over to John.
Okay, thanks, Matt. I'm glad you mentioned that it was Beaufort, not Beaufort, which is in North Carolina. Beaufort's in Best Carolina. So what I want to talk about today is how we use the DNA testing process, or how we use TrueAllele basically to overcome bottlenecks in our process and improve data recovery. And that's a long wordy title, but basically all we're doing is using the computer to help us figure out where to go. So just to go through, let's see, just to go through this real quickly, just to reiterate or refresh ourselves on our goals, I just wanted to go over what we would normally consider to be the goals of DNA testing, which obviously would be number one, helping to identify perpetrators of crimes, eliminating wrongfully confused, and helping to prevent future crimes, presumably by identifying these people quicker. We need to be able to test these items faster because we want current crime to be solved, obviously, number one. Number two, we want to rule out those who are innocent. Number three, in order to prevent future crimes, we need to identify the current perpetrator as quickly as we can. So if somebody's innocent, obviously you also want to get that person cleared as quickly as possible. So how do we do all of that? Well, historically, there's been two ways that we've done that. Number one is obviously hire more people. And number two is to automate as much as we possibly can, keeping humans restricted to tasks that require intelligence or abstract thought, and having machines for repetitive processes. And automation in our laboratory, or in yours and in all of our laboratories, is really nothing new, right? This goes back about 20 years to the old single capillary genetic analyzers. But I think what's noteworthy here is that really it's the first and last steps that have to this point remained human operated. So in terms of identifying material for testing, there's really nothing or no way that we can automate that right now. That still, as I mentioned, requires abstract thought. But what about data interpretation? So if you figure that, we're looking at typically 96 well plates, and if you use that plate to the maximum efficiency, you're looking at about 80 to 90 DNA profiles on each plate after you account for controls and ladders. And since we're talking about human interpretation here, I'm going to head over to the 2017 SWGDAM guidelines, where this comes up when it's discussion for human interpretation, that in summary, evidence samples excuse me, should be interpreted before comparison to knowns so that we can avoid any kind of confirmation bias. We want to know what the evidence genotypes are and interpret those without being influenced by any knowledge of the known samples. And so again, a stepwise process for this is, looking at your evidence profile first, figuring out what your genotypes would have to be without the knowledge of any known types, comparing the DNA types to your knowns, and then determining if a match exists. I should also point out here too that when we talk about inferring DNA types without evidence, or I'm sorry, from the evidence without knowledge of known types, we're also talking about other evidentiary profiles, right? If you have, say, a single source profile from one piece of evidence on your case, and you have a 3-person mixture on the other piece in your case, when you're interpreting that mixture, you really shouldn't be having any knowledge of that single source profile. And that's really hard, as you well know, to try to eliminate that from your mind, but it should be done. So getting back on track, getting back to the DNA data, if we're looking at a full plate of data, doing so as to avoid any type of confirmation bias, how long is it going to take us to interpret that full plate of data? Well, if you work from a typical, workday, an 8-hour workday factors in or calculates out to 480 minutes in the day. And let's say we're going to look at 84 DNA profiles. If we're considering 84 profiles, on a plate, between 80 and 90, so let's just say 84, that's a nice even number, and 480 minutes in a workday, we're looking at about 6 minutes per DNA profile roughly for interpretation. So you're looking at about, if you do this 8 hours straight, right, no bathroom breaks, no answering emails, no phone calls, could you do 84 profiles? Could you interpret a whole plate in an entire day? I mean, if they're single source samples, yeah, you can, of course you can do that. If they're 2-person mixtures, well, maybe, but you might be pushing it. It depends on how complex they are. Are they roughly equal in weights? Is there possible degradation of one or some dropout? So as your complexity increases, your ability to interpret all of this in that span of time decreases. And then if you start throwing in 3 contributor mixtures or even more, no, I would say that this is highly unlikely that you could interpret, that a human, I should say, can interpret a whole plate in one workday. So what you end up with then is a bottleneck, really, caused by the volume and the complexity of the data you produce, right? And then if you're talking about human interpretation, of course, you have to deal with various thresholds, stochastic thresholds, analytical thresholds, dropout thresholds, and everything like that. You could hire more people for interpretation, right? If you've got a lot of data, you could always bring in more people, but really all you're going to address there is the volume of the data, not necessarily the complexity. So what ends up happening typically is that a lot of data just end up being declared as inconclusive, right, or too complex for interpretation. There's too many contributors. We can't do anything with it, basically because we don't have the time or the ability to sort through it. So it just gets tossed out. And, is throwing out data, the only way to do it? Well, to steal a line from Yoda, no, there's another. And that other way is to automate everything. It's automate the data interpretation using computers, right? Let human beings do what they do best, let machines what they do best. And so what we can do is we can automate DNA interpretation with computer technology, which is what we do in our lab. That's how we've implemented this. And you've probably seen this image before. As I've said before, they say that flattery or imitation is the sincerest form of flattery, but in fact, plagiarism is the sincerest form of flattery. And I lifted this directly from other cybergenetics presentations, so you've seen it before. But to go over it again, we analyze our DNA profile data in our viewer client workstation. We use that data to create requests for the computer to solve. We upload those requests to the server where the computer solves them, and then the computer performs automated matching while we walk away and do other stuff. So when the computer's finished, we download the results to the client computer, and we either proceed to more detailed processing for confirmation, or we determine that the testing is done and we write the report. So this is how our process works. We take an entire plate of data and upload that entire plate to a single database world on the server. So everything on this plate goes up to the server in batch requests. You can run this batch request during the day while you're doing other stuff. You can run it at night when you're at home. You can run it over the weekend, however you want to do it. And so the computer then interprets that data, it solves everything, and it looks for matches. When the computer's finished, the human operator checks the results. So you're checking to see what do you have in comparison to other data files on the same plate? What do you have in comparison to other known profiles that are on that database world already, and to previous runs, to previous evidence samples? So you're going through, this is an automated feature. You just ask the computer, basically find a match, and it will find a match for any type of sort criteria that you want to look through. You can set a log LR to a certain level. You can look within a case. You can look between cases. You can look only at matches to reference profiles, to staff profiles, what have you. There's a lot of flexibility in this. And then if any probative matches are returned, and by probative we mean something that provides information on the case, then the operator can go back and create more specific and detailed requests for reproducibility on a separate world to confirm that match. And so this is what the benefits that we have accrued. First, everything's being examined. All the data is being looked at. There's no thresholds being applied. There's nothing being discarded. There's nothing being ignored. Speed, this entire plate, our server setup can do this entire plate in about 6 to 7 hours. It's not getting distracted. It's not taking phone calls, etc. And while it's solving, the operator can do other work. This is a big one here too. There's no confirmation bias. The computer interprets every profile separately from all the others. So it looks at each individual sample file separately with no consideration for what the other sample file in, say, the well to either side of it was. There's no bias to what the profile should be. There's no knowledge about what the other profiles on the plate look like. And there's no knowledge about any reference profiles in that case. All the data is compared to everything else. So everything, major contributors, minor contributors, every contributor in the sample, they're all compared to all the reference samples in that world, all the lab staff, crime scene investigators, any lab controls you might use, which allows you to identify more case-to-case matches and more potential contamination events. And the last thing that we use it for is for CODIS specimen assessment and candidate match assessment. And I'm going to spend the rest of the time talking about how the database, this workflow has helped us in these areas. So just as a little bit of background, we started casework with Trulio in January 2016. We had an older server that we had purchased a few years earlier that we validated on, and that server really ended up being insufficient for the volume of cases that we were testing by the time that we got testing implemented. So in 2017, we expanded our server and we now have a total of 28 processors. So Matt was kind enough to come down and help us set this up. And the way we have it is we have on our expansion modules, we have the 20 processors from the new servers that will work either casework or database requests, depending upon the order that they are in the queue. And then our original processors from our first server, the slower ones, are dedicated strictly to database screening because we don't want these older, slower processors running, long casework requests on these expanded loci kits, which, as you know, can take a little bit of time. If you're familiar with the Trulio user manuals, you'll know that in the user manual, there's 2 workflows described. The first one is the casework workflow, which you work items selectively on a sample by sample and a case by case basis, right? You take individual sample files from individual cases, create work requests on those individual files, and then determine if you have matches there within your case. The other workflow is the database workflow, in which you batch upload the entire run file, or the entire run folder, excuse me, to an individual database world. You look for matches, and then you go back and you take any matching samples to the casework process for confirmation. In our lab, we decided to go ahead and implement the database workflow for 2 reasons. Number one, to make sure that we weren't overlooking anything in our data, to make sure that we were getting the most information out of it that we could. And number 2, really just to make a more efficient use of our time. We do a lot of touch samples here. That's the majority of what we do. And we were ending up, putting a lot of our run data into Trulio anyway, because they were complex. We first thought, well, we'll eliminate visually, and if we can't eliminate something conclusively, then we'll upload it to Trulio and we'll have Trulio tell us. Well, because of our data, we ended up putting a whole lot of our stuff into Trulio anyway. So we thought, hey, since we're going to run this data through anyway, why not just do it on the front end, do it in a short databasing run, and let the computer tell us whether or not we should proceed. and on what items we should proceed with. So after implementing that process, we decided to go back and just go all the way back to 2010, all of the data profiles that we have, to go ahead and batch upload everything up to our TrueAllele database, which resulted in excess of 15,000 inferred genotypes. And this is the request conditions that we ran this on was 5,000 cycles burn in, 5,000 read through, and we ran everything at 3 contributors. Our current process, we will decide, is it a 1 contributor, 2 contributor, or 3 or more contributors for our databasing. But for this historic data, we really didn't want to take the time. It wouldn't have been worth it to go back and try to figure out the number of contributors for all these. So we just set it at 3 and uploaded them and saw what happened, which came back with, for EVI to ref, at least around 30,000 potential lines of data in an Excel spreadsheet, but went through all of these, and most of these were within case. So we're talking about matches of items to elimination standards that we already knew about, or matches to suspects in the case which had already been reported. But we found around 80 previously unknown EVI to ref matches from case to case, which we're still sorting through and we'll end up having to report. But you look at it and you think, wow, geez, 30,000 lines to come down to 80 cases, but those are 80 cases that we didn't know anything about. We had no idea that they were matching at all. One interesting set of cases that we found was this, and there were 5 samples from 5 different cases that matched each other in an EVI to EVI search with no matches to any other genotypes in the database. So in other words, these 5 genotypes were only matching to each other and not to anything else that we had. And this is shows you the log LR scores for these 5 matches. I just decided to pare it down to comparing the 4 cases on the left-hand side to 1 case on the right-hand side. And you can see that there are some really strong matches here. You've got a log LR of 14.7, one of 12.5, and then some that are lower, 8 and 6. But in seeing these, the next step was to figure out what's going on. So we went back and looked and evaluated the cases and determined that, I mean, right away, these are cases that kind of, I mean, they could be kind of similar maybe, except for that last one, car break-in. But really what was more interesting to us was that 4 of these cases all had known suspects. So you're looking at 2, 4, 7 different names on 4 of these cases. With the first case obviously being an unknown suspect, but 7 different names. None of these suspects were in common. They did not match to each other at all. In addition, the 2015 attempted murder and the 2016 murder case, the identity of these people was not in dispute. It was the circumstances that were in dispute. But as for who the suspect was, there was really no question. And then in fact, the car break-in in 2017, these people were witnessed and caught almost immediately after the event. So this was very strange. So we started thinking about, okay, possible causes. What happened here? Is it possible that we have, 1 person committing all these crimes and that we have 7 people that have been wrongfully accused? Well, probably not, especially considering you've got 2 cases where it's the circumstances that are in question and not the identity. Is there an accomplice, some person that we don't have a standard for, somebody we just don't know about? Maybe, you start thinking, did we do something in the lab? Have we contaminated something somehow? Well, I mean, possibly. I was watching X-Files, so I thought, maybe it was aliens that did it. I don't know. The truth is out there, I assume. So we decided to go through an investigation to find out what the truth was. So the first thing that we do in a situation like this is to assume that we did something wrong in the lab and try to work backwards to determine where that error was made. And if obviously, as you're working back through, if you can rule certain things out, then that gets you closer to the answer. So the first thing we could say is, number one, these were worked in the lab at different times by 3 different people. The genotypes don't match the lab staff, anybody that works here, and they don't match any other case reference samples in our database. So that started pointing us in a different direction. We look back, where did the cases came from? Well, it was all the same agency that tested them. They're all touch DNA samples, so there's no body fluids here. And all the evidence was collected or handled by the same investigator. And in fact, this one investigator was the only common link that we could find between all the cases that we had. So then we requested a reference standard from this investigator. And you probably at this point aren't surprised to see now that he matches to all of these cases, right? With some really strong log LR scores. But here's the interesting one here at the bottom. You see a KL here of roughly 17, but a match score of only 4, and that's a pretty big spread. And so the question that, in order to, I guess, the question we ask is, okay, that's a pretty big spread. How do we figure out what's going on? Well, then we have to go look at the data. So just as a reminder, the batch request conditions that we used here for this historic data was 5K, 5K run, 3 unknown contributors. So here's the data from the data window. Right away, you can see that we've got a pretty low signal strength and it looks pretty complicated. Maybe there's some degradation going on, I don't know. There's multiple contributors. It's run as a 3 unknown, but when you look at the convergence scores, you can see that they're not where we want them to be, particularly for contributor 1 at 1.6. This is the contributor, in fact, that matches to the investigator. And so you can see that the computer probably didn't have enough time to resolve this kind of data. Is 5K, 5K, is that something that you would normally run in a casework situation for this data? We wouldn't. It would be run a lot longer than this to try to resolve this. The second thing too, here's 2 of the loci. Remember, it was run as a 3 unknown, but are there 3 contributors in this sample? Well, no, there's clearly not. So that explains, at least to us, why there was such divergence between the KL and the match score, and that the KL was based upon solving for 3 unknown contributors at a very short runtime, whereas in reality, if we were doing this casework processing, we'd have at least we'd probably run it at 4 and 5, maybe 6 possibly, to see what we could get out of it. But the run conditions, again, and it's fine, because this process, this database workflow, again, we're not using this as a definitive solution. We're just looking for potential matches for further investigation. And the way I think of it is similar to like a presumptive test, right? We're using this as a presumptive test to sift through a lot of complex data and look for possible matches that we'll look at more in depth. Instead of spending a ton of human time trying to interpret every possible contributor that might be there and then comparing the knowns, we just let the computer do the heavy lifting and then tell us which samples warrant a closer look. And what we found here is that this was really great for quality control as a procedure, right? 2 of these profiles had previously been entered into CODIS, and we did get a match in ELDIS. But I don't recall which cases they were, but we didn't think anything of it at the time. It may have been one, I think one of them was the unknown suspect and one was the other, in which we reported the information out and never heard anything back on. Obviously, if we'd had the reference sample beforehand, we could have identified through CODIS that this was the investigator, but the other 3 profiles we had were unsuitable for entry. The one that I just showed you was one that obviously was not entered. But the bottom line for this investigation, at least, is that this is how we can use TrueAllele and the databasing process as a quality control mechanism, right? Especially if you have all your lab workers and all your crime scene investigators in a staff database, because then you're comparing every piece of your evidence data to the staff database and not just the pieces that you selectively enter into CODIS. And it works that way for lab quality control as well. Maybe if there's an event that happens in your laboratory that you don't know about, you can identify it through the databasing process. So looking at CODIS match evaluation, this is slides. This is a CODIS profile that our process was able to resolve. So this was one that had been databased. It's a forensic mixture. It went up to Endus. The match estimator told us that we would get one match in the database, and we ended up with three offenders. But I'll direct your attention here. So what you can see is that after 30 minutes of human review, the human reviewer could not eliminate any of the 3 offenders, right? 1 was uncertain, 2 could not be eliminated. But with 5 minutes of true allele work, the computer was able to eliminate 2 of the offenders and identify a match to the 3rd. And really, when I say 5 minutes of true allele work, that's actually not accurate. The 5 minutes of work was actually spent by the human operator converting the offender profile into a text profile and then importing that into true allele, because the computer had already resolved the mixture. It was just that we had to translate, I guess, the offender profiles into text. And then if you look in the 3rd column, I placed the likelihood ratios for all the candidates, and you can see there's a huge spread there, especially in comparison to the CPI of 1 in 39,000 for all 3 versus a match score of 73 billion for the last one. And keep in mind too, if you were using CPI for your match statistic, you would be falsely including offenders number 1 and 2. They're not there. This is a second example of how our automated process resolved the CODIS mixture. And what I want to show you here is that you've got an MME here that's roughly 2 times 10 to the 4th with a CPI of 65, but the LR is 158 trillion. So there's a lot of good information in this mixture, even though you have a pretty small MME. So going a little bit further with this, we had in our databasing run, we had some previously unidentified matches, some ones that we didn't know about. In 2014, we had a burglary case that was uploaded to Estes. We got an offender hit on it, and the match was confirmed in the lab. After processing all of the old data in 2017, we uploaded to TrueAllele and found 3 additional cases from 2012 to 2014 that ended up matching this reference sample. But they had never been entered into CODIS. And so that was a bit disturbing to us. And we asked, why were these samples never put in? If we're getting 3 additional cases from the same time frame, why did these never go into CODIS? Well, so we looked at that and plotted them here, and you can say, first off, there were at least 3 contributors in each mixture. There was no major contributor in any of them that could be deduced. At the time, we were still operating under the 4x4 rule, excuse me. So between the lack of a major contributor and the 4x4 rule, we couldn't enter anything. If you look at the CPIs, again, the calculated CPIs are very low, but the likelihood ratios are very high. So there's a lot of match information in here that we can use. So we just asked, can we use the automated process for CODIS screening? Since we have already, we've already run these in a screening run, a short run to try to resolve what the inferred contributors are, can we take the information that the computer has already generated for us and use that to help us put profiles into CODIS? So one of the tools we looked at for this is the KL that TrueAllele calculates, just as a reminder that the KL basically measures the information value of the inferred genotype. So you have an idea of how strong or weak that match information is for the inferred genotype in question. The other tool that we thought about using was the MME, right, that the CODIS software calculates for you, that predicts the number of matches at moderate stringency for a database of a certain size. So we decided, well, let's compare the MME, the KL, and the likelihood ratio for CODIS profile assessment and see what we get. And this is a graph for the results of the 5 CODIS profiles that I have just discussed in the last few slides. The first column in blue is the MME in log scale. So 10 to the 6th, 10 to the 7th, 10 to the 8th, and so on. The middle column in red shows the KL from true allele, and the green column in the right shows the likelihood ratio in a log scale. So in looking across all the samples on this graph, you can see the KL and the likelihood ratio, the log LR, track fairly well. As the KL goes up, the log LR goes up, and as the KL goes down, the log LR goes down. However, the MME and the log LR really don't track well at all, which you can see best right here. You've got 2 MMEs for both of these samples that are both fairly close. They're both right around 10 to the 8th, but the log LRs differ by almost 5 orders of magnitude. And then if you look at this last sample, particularly in comparison to sample number 2, the one from 2013, you can see that the MME here is 10 to the 4th, which is about 4 orders of magnitude smaller than the sample 2, the 2013 sample, but the log LRs are comparable. So what this is telling us right off the bat here is that the MME, while it may help you determine how many matches you can find at moderate stringency in the database, it's not predictive really of the quality of the data that you're putting in. So our conclusions from this were to use a combination of the KL and the MME to search for offender matches, basically by starting out by looking at the KL. So if we get a high KL, that's indicating to us a high degree of match information. So for inferred genotypes with a high KL, we'll use true allele to help us build an MME that allows CODIS to filter out adventitious matches. We use the genotype confidence function to sort out the combination of genotypes that will add up to the selected probability that we want to use at. So I think the default is 99%, the default view, but you can change that to 90%, 95, 98, whatever you want to set it at. But what we do is we identify enough alleles that we can enter into CODIS so as to avoid mismatches, but not so many that you get a bunch of adventitious matches that you have to sort through. And then inferred genotypes with a low KL, they don't have a whole lot of match information anyway. And in our experience, as we've tried to do this, they don't really lend themselves well to building a useful MME. So we don't really upload these. We also are fortunate in our state that our state CODIS administrator has built for us a specimen category of probabilistic genotyping. So this one that she's built for us has I think it's a maximum of 8 alleles per locus with no MME requirements. So that's sort of our, I guess, last resort method. We try to use this particular process to build an MME that will at least get us to the state forensic partial or our state forensic mixture. And if we can't do that, then we'll put it into the probabilistic category. But so far, most of the things that we've used this on, we've been able to get them into one of the more stringent state categories. So the summary, DNA interpretation can be automated with computer technology to reduce or eliminate bottlenecks caused by the volume and complexity of the data, and we don't have to use thresholds for them. There's no need. The output from this automated process can be searched internally and also screened for CODIS profiles and for assessment of candidate matches. And this process considers all the data in the sample, which ultimately allows the operator to recover more information from the same amount of data. So you're starting with the same amount of data, but you're getting more utility out of it. And because we're letting the computer do all the heavy lifting, it gets time back for us to perform other tasks. And so without, I guess, anything else, that's it.